Hi, welcome to BC Video 10.5C Part 1, Points of Intersection and Polar Arc Length.
Okay, so we're not finding the areas for these. The question just asks you to find the points of intersection of the graphs. Now the key thing is, of course, they mean all of the points of intersection. One would think that by solving a system of equations like we do with rectangular functions that we would be able to easily find all the points of intersection. One would think, but that doesn't quite happen. So let's try it. Sometimes it will give us all of them and sometimes it won't. So in this particular case, you have two cardioids, okay? You have the red one and the green one, and we're looking for their points of intersection. Now, one of them is obvious, it's the pole. And by the way, when you're naming the pole, don't bother naming it as 0, who cares what, just call it the pole. Again, here it's very obvious that the other 2 points of intersection are at the intercepts, which both happen to be 3, 0, 3, pi. But let's actually solve the system, see what we get. First of all, I would multiply through the 3's. They're both equal to r, they're equal to each other. Divide through by 3, the ones cancel. You're left with 2 sine theta equals 0. So sine theta would equal 0, and that happens at 0 at pi, etc. So there's the 0, there's the pi, and then the others are just repeats, right? So these are all the same points. So there are 3 points of intersection, and here they are. Now, use the TI to graph the polar equations and approximate the points of intersection of the graph. Confirm analytically. Unfortunately, on your calculator, when you're in polar mode, there is no intersection feature, so you actually have to solve the system of equations as a single equation. So, what you'll do is you'll set the 2 equations equal to each other and solve that on the TI. So here, for example, if we have these 2 graphs, and you wouldn't need to know how to graph this by hand. It turns out it's a sideways parabola. But you have your calculator, so we're going to solve the right side of this one equals the right side of that one. Now you're purposely going to do it, sorry, that should be theta, not x. You're purposely going to limit it to 0 to 2 pi, because otherwise you'll get that weird answer. Now what you're going to get is theta is 1.998 or 4.285. You're never going to get these answers, I don't think. Yeah, they wouldn't be nice, pretty answers in exact form. So, for each of these, if you plug them in, you'll find out that r is 4.243. So where are these? Well, of course, pi over 2 is 1.57, pi is 3.14, and 3 pi over 2 is 4.71. So the 1.998 would be about here. That's the point of intersection right there. And the 4.285 would be in the very close to 4.7, which would be down here. So those are the 2 points of intersection. And as I said, when you plug these into either equation, you'll get r equals 4.243. Now, before we get into elusive points of intersection, I do want to go over polar arc length. So recall that we've already done rectangular arc length in section 7.4. I hope that's the right section. Remember, that was the integral from a to b of the square root of 1 plus the square of the derivative of f prime of x. We also did parametric arc length just recently, and that's the integral from t equals a to t equals v of the square root of dx dt squared plus dy dt squared dt. So for polar, it's really going to be quite similar, okay? Let me show you this one first. What you have is, instead of t, it's theta. So instead of a and b, we'll say theta goes from alpha to beta. And you have the square root of the square of f of theta. So if you think about it, if r equals f of theta, then dr d theta equals f prime of theta. Okay? Oh, I'm sorry, that would be equivalent to that. So what happens is this. Our r, which is f of theta, remember that our x, if we did it in terms of x and y, our x is r cos theta, which is f of theta cos theta. So therefore, if we looked at our dx d theta, where am I going with this? And that would be your y equals r sine theta, which is f of theta sine theta. So now, oh, I'm seeing where I'm going with this. Now we have dx d theta. We have x as a function of theta, and we have y as a function of theta. So what happens is, if you think of it this way, it's the integral from theta equals alpha to theta equals beta, which are, of course, lines through the pole, square root of, and instead of dx dt squared, it's dx d theta squared. Instead of dy dt all squared, it's dy d theta all squared, d theta. Now another name for dx d theta squared plus dy d theta. I must show this on the next page. Where am I getting r squared plus dr d theta squared? I don't know. Let me see if I have it on the next page. I do not. Okay, possibly, this is probably, I'm guessing, it's one of those long explanations as to why it's equal to this. But I really don't want to get into that right now because that'll take too long. So just trust me on this one, that it's the integral from theta equals alpha to theta equals beta of the square root of r squared plus dr d theta all squared d theta. Okay, so r squared and then dr d theta squared. So let's look at an example. 55 through 60 are by hand, and 61 through 66 are with the TI, and we're dealing with polar arc length. Okay, so number 60, it's asking you to find the arc length of the entire cardioid. You have to notice that there's a sharp turn here, and because we're going to be integrating, we can't integrate across a sharp turn. So you are absolutely going to have to, although I did do it over a sharp turn. Right, here, sorry. The rest of it is all the algebra of doing the actual integration. So because of the sharp turn, although you would like to do 0 to 2 pi, because it's not smooth at pi, meaning it has a sharp turn at pi, you are going to have to do 2 times 0 to pi. And as you can see from the shape of the figure, 2 times 0 to pi, it is symmetric with respect to the polar axis, so we'll be fine. Okay, so here's our formula. Our r squared was 8 plus 8 cosine theta, so our r squared is the square of that. Dr d theta, if you take the derivative with respect to theta of this r, you'll get 0 plus 8 times negative sine theta. So negative 8 sine theta, which we square. Now I'm actually going to do this integration. For now I'm leaving it at 0 to 2 pi, but then at the end we realize we can't do that. Alright, so we square this, we get the following. We square this, we get that. Here I can factor out the 64, which is extremely convenient because cos squared plus sine squared is 1. At that point I add the two 64s. I can pull out a common factor of the square root of 128. Now, this is tricky, okay? You would have to know that you have to multiply, because you can't, there's nothing you can do with this. You'd have to multiply top and bottom by 1 minus cosine theta. So if it was this complicated, either it would be bonus, or I'd allow you to have your calculator, in which case all you'd have to do is enter this expression. Oops, 2 times 0 to pi of this expression on your calculator. Okay, but if we do follow through with this, if I multiply the tops, I get the square root of 1 minus cos squared over the square root of 1 minus cos. At that point, you would say 1 minus cos squared is sine squared. The square root of sine squared is sine theta. And you would then be able to let u equal the contents of the radical. The derivative would be sine theta d theta. You're actually looking at 1 over u to the half, and you integrate that, blah, 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 blah. And remember, it's 2 times 0 to pi, so it's 2 times that 2 here times the square root of 128, and you will get 64.